Hope everyone is full of energy. I know I am. This is why I'm doing the slides, because then I can go faster, right? No, actually, I wasn't sure if there would be a blackboard, so I'm going to talk about transport in topological insulators. And I'll start with a brief introduction, which was supposed to be basically a summary of what other speakers hopefully would have talked about, and mostly they did. And then I'll go to transport. So, how are your energy levels, actually? Is anyone tired? Because if you want, you can stand up and shake a little bit for like 1 minute. No? Okay. So ask questions if I go fast. Now it's especially important now because I have this device which makes me go fast. So I don't have a intrinsic damper. So you have to be the damper. So you have to ask questions whenever you don't know what I'm talking about. Okay? So start with an intro. So how many? I was going to assume that you know. I mean, there is this. Okay, it's okay. You can read it. I'm not going to move this. So I was going to assume that you basically know that topological insulators are bulk insulators with metallic surfaces, and at least today, most of my talk is going to be about trying to explain what does this mean, a metallic surface, a little bit more carefully than just the metal. And actually, most of these things were explained. But if you haven't seen this before, this is an insulator. So I just write 2 bands here. And I have assigned some topological quantum numbers to the bands. And this could, for example, be the Chern numbers that you heard of. So if you calculate the Chern number of a band, it has some number. And the fact that it's topological means that if I try to transform this band somehow, meaning I add some perturbations to it, as long as the gap doesn't close, these numbers remain the same. So on this side, I have the vacuum where these numbers are 0 and 0, and on this side, I have the topological insulator, which is characterized by having a different set of numbers than the vacuum. Now, the fact that the numbers cannot change if I am kind of moving my bands means that somewhere, if I now think of position, I think of moving from the topological insulator into the vacuum, then at some point, the gap has to close, and there's a gap closing point at that point, which is at the surface, and there I have a gapless state. And that's the metal that I want to understand and I want to discuss. Okay. Now, these guys come in various guises, and I was hoping Alex would show this, but I guess you'll do next time, in next lecture. So I don't plan to explain any of it, or most of it I'm not going to explain, but you see here T, and I changed this from P to C so that I will be consistent. And the S, this is just what Alex already discussed. And then you have these classes here, which are basically, they are either integers or C2 numbers, which characterize the different insulators. In my talk now, I'm going to mainly focus on this class A2, which is characterized by having time symmetry as squares to -1, and no other symmetries. And these are the ones we usually call, or if you say topological insulator without qualifying, then often you mean these guys. And I'm going to talk about very briefly in D equals 2 dimensions, the physics of D equals 2 dimensions, mainly because that's most of the stuff you'll do hands-on with Michael Wimmer will be 2D because it's doable in finite amount of time. And then most of my interest will be in discussing the 3D physics and generalizing from that. Okay. So time reversal. Thankfully, I don't have to do this. I can do this very quickly. There are 2 types of symmetries, unitary, anti-unitary. This I will use later. So this is the definition that you already saw. earlier today, we can always write time reversal as a unitary times complex conjugation, and the time reversal is squared to plus or minus 1. So it's nice to see how this works, actually, and to be aware of the fact that complex conjugation is a weird thing. So it's a base dependent. I have to define complex conjugation with respect to some basis, and generally we define it with respect to the position basis, which means that x is real. So x is real, it goes into itself, which means that the momentum, which is minus I times derivative, goes into minus itself. So that this way, complex conjugation does what we want it to do if we are on the right basis. If you have spinless fermions, and what I want time reversal to do is to take x to x and p to minus p. Now, if I have spin, I need something more, and what I can usually do is, and this could be pseudo-spin, it doesn't have to be real spin. I have some matrix here, I sigma y, and complex conjugation, this squares to minus 1, as you can verify over cocktails. Now, x and p don't care about the spin, so they do the same as before. But now what has to happen to the spin and the time reversal? So make sure that you're awake. Change the sign, why? It's an angular momentum, exactly. So if x goes to x, p goes to minus p, then x cross p should go to minus x cross minus p. So, and you can just check that this matrix does the trick. The reason is that sigma y is imaginary, so k flips the sign of it, and then sigma y flips sigma x and sigma z. Okay, good. Yeah. Well, I mean, you can make, no, I said complex conjugation is basis dependent. You could make a complex conjugation operator defined such that p was real, and then x would go to minus x. This would not be what we think of as time reversal, but I can easily define this operator. But when I say complex conjugation, I have to say with respect to what is it real. And generally we don't bother saying it, and it's always in the position basis, but then, okay. That was the intro, in the sense that this was the stuff that I expected you to know from the lectures before, and I think it was basically all covered. Any questions? We're fit? Okay. So 2D topological insulator. So what I now want to do is to try to understand a little bit this surface state that I told you there is. Because I have topological insulator, then there has to be a surface state which is metallic. Now, what does it do? What does it mean that it's metallic? And let's start with something that most of us may be familiar with, hopefully. This is the quantum Hall effect. This is the first, in a sense, topological insulator. Here's Hamiltonian for it. If I take T to be K, then P goes to minus P. This is not symmetric. It's not time versus symmetric. Time versus symmetry is broken. If I try to solve this, I get lambda levels. So if I put my chemical potential somewhere in between the lambda levels, I have an insulator. But if I have a boundary, then we know that at the boundary we get edge states. I don't know what happened. So the lambda levels spend at the edges, so that means we get these edge states. And now if I move my chemical potential, let's say I go from here to here, I move between two different insulators, and actually exactly at this energy there's the topological quantum phase transition between two distinct topological insulators. And I change the number of edge states from 1 to 2. I go here, I have 3, 4, and so on. And because these states are chiral, they only move in one direction. That means that if I add some perturbation, if I try to kind of degrade the conductance of these edges, they don't care because they just go around it. Because they all move in one direction. If I wanted to scatter them back to kind of make them not move, they have nowhere to go. Which is why the conductance, this is the whole conductance is quantized with nu, the number, which is a step number, which is just counting the number of lambda levels. And if I were to do a two-terminal conductance measurement, it would be the same. Okay. So here, kind of the fact that the surface is chiral means that there's no backscattering, there's no localization. This metal is a very, very good metal. But this is a more general statement, which we'll try to understand a little bit better how it comes in other cases. In particular, if we go to time reversal symmetric systems, namely quantum spin Hall effect, here's the Kane-Melley model of quantum spin Hall effect. If you have seen it, great. If you haven't seen it, doesn't matter. All you have to know is that it's time reversal symmetric. The t squared equals to -1. And it has a band structure that looks like this. So there is some bulk states, but then there are these two edge states here, which live like this. There's one moving to the left, I guess that's right, and one moving to the left. There's one moving to the right, one moving to the left, on each side. So now you might think, well, if I add some dirt to this thing, then the conductance would not be quantized anymore, and I could, in principle, couple these things together such that something happens. But it turns out that you cannot. So let's do a calculation that shows that. I want to ask, I have a wave function psi, which is, let's say, the right-moving one, and I have some potential v, which can be anything as long as it doesn't break time reversal. Because if I break time reversal, then I'm living under the constraints that I want to have a time reversal symmetric system. And if I ask what is the matrix element of this potential v to the wave function t times psi. So what is t times psi? If psi is the red one. Moving left. It's the one moving the other direction, yes. So if I reverse time, then I take a right mover to a left mover on the same side. And as it turns out, I flip the spin. So let's see. Let's calculate this. First, I'm going to use the fact that T is an anti-unitary operator. So this is the definition of an anti-unitary operator. If I multiply both psi and T psi by T, actually V T psi, then I get a complex conjugation. And there's one warning. When you're using anti-unitary operators, then Dirac is not your friend. Because Dirac kind of somehow implicitly assumes, well, not himself, but the Dirac notation, assumes linearity. So you can make mistakes if you just go ahead and do stuff that you usually do. So when you're calculating things, it's best to only use this formula and never take, make an operator into its Hermitian conjugate without, that way you make mistakes. So what I just did is I thought of this as a cat, this is a cat, and I had to multiply by t. This is the reason why I'm putting t here, but not on the other side. So, t anti-unitary, with a warning. Okay? Now I'm going to assume that v is time reversal symmetric, and therefore commutes with t. Therefore, t times v becomes v times t. Now I can take this t and multiply with here. I have t squared, that gives me a minus sign. Now I have t psi, v psi complex conjugate, which if I take complex conjugate, if I flip it around, I get this. So I get this matrix element is minus itself, and therefore it's 0. So there's no backscattering. The fact that this is 0, that means there's absence of backscattering. The conductance is 2e squared over 8. Because no matter how much dirt I put here, assuming I'm not doing anything that breaks phase coherence, I will get conductance 2e squared over 8. Now what would happen if I added a second pair of edge states? Could I repeat this calculation? Yes. Of course. Would it be true? Yes, it would also be true. But it would only tell me that this state cannot be scattered into this state, which is the time reverse of it, and this one cannot be scattered into this one, but this blue one can be scattered into the red one on the other pairs. And therefore, they can couple together, and they can gap out, and then they can disappear. And therefore, a time-reversal invariant quantum spin-Hall insulator with nu equals to 2 does not exist. There are only two 2D time-reversal invariant insulators. It's a trivial one, and it's the quantum spin-Hall effect. That's where the C2 comes from. Yeah, this is a phase coherent calculation, so the system has to be smaller than the phase coherence length. And a couple of other things, but I'll get to it in a second. It's a good question. Okay.
Well, I have a question.
Yeah.
Where do we see that say that the first blue doesn't couple with the second red?
You mean in this case or in the?
Like now.
Like now. Well, it does. It can. That's why this cross.
So where do we see that it does couple?
And that it does couple. So this calculation here, I have to put T psi here. So it's psi and T psi. And that is the first red related to the first blue. If I take the second red, then this will give me the second blue. But there's nothing like this that will relate the first red to the second blue. Clear? Okay. So experiments have been done. I measured it. They get 2e squared over 8. Fantastic. Okay, there's a logarithmic scale, but let's come to that later. Except that they don't measure the 2-terminal conductance. They measure the 4-terminal conductance. So then let's calculate the 4-terminal conductance. What's the 4-terminal conductance? That's saying, okay, I pass a current from here to here, and I measure the voltage between here and here. I can calculate that by just using the Landau-Böttiger formula. How many of you know it? Okay, I think it's sufficient numbers. But it's basically saying that if I want to know the current in one lead, I just have to know let's say, the current going into lead 1 coming from lead 2, I just have to know the voltage difference between them. And the transmission probability going from lead J to I. Okay, so I want to calculate now current going from lead 1 to 4, voltage between lead 2 and 3. The fact that the current is passed from here to here means that the current in lead 1 is equal to I. Current in lead 4 is equal to minus I. Because if a current goes out here, it must go in here. And the fact that these are voltage leads means that there's no current going through them. That's a definition of a voltage lead. It only measures the voltage, it doesn't take out any current. Now I'm allowed to put one voltage to be the ground, so I take V2 be to 0, and now I'm interested in knowing what is V3, which is the voltage which I call V here. And the conductance that is measured is I divided by V. Okay, so now we just have to plug these things into here, using that since these guys don't get backscattered, the transmission probability of the red one to go to 2 is 1. 1 always goes to 2 and nowhere else. 2 always goes to 1 and nowhere else in the blue one and so on. So the transmission probabilities are either 0 or 1. So I do the calculation. First of all, the current in I is the current coming from 2 and from 4. So I can get current from 4 and from 2. And if I plug in the conditions that I had, I get this expression here. Do the same for voltage lead 2. There's 0 current coming in here, but the current that comes in here comes from lead 1. That's why there's this term. And it comes from lead 3. That's why there's this term. Okay, now I write it down. It's maybe a little bit fast, but that's okay. I hope. Yeah. Can I say maybe something about that a little bit later? Can I? If that's okay. Yeah. No, actually the Jacobi experiment with the superconductor and the Fraunhofer effect is very nice, I think. You can kind of extract the current profile from it. I think we maybe should discuss this over like beverages. Okay, so now we have these equations. I'm sorry if this was too fast, but it's basically just adding in the current and voltage that I added before. And I just wrote down the 4 equations starting from the Landau-Böttiger. Now I have this equation. 0 is equal to minus V times V, so that means V1 is equal to minus V. This gives me what V4 is. If I plug that into here, where the current, I can get that the current is minus 4 times V, so G is 4E squared over 8. Oops. That's too bad. Maybe I did something wrong. Anyone? Actually, when I was younger, still young, I think, I did this calculation and I was really confused when I got 4. And the reason is that, unlike the quantum Hall effect, where it doesn't, I mean, here I just put a voltage state here and here. It matters that in the experiment, actually, there are other voltage states here and here, even if they are not measured. Because that changes the current distribution between here. So you see the current now goes into this lead, and now from there it could in principle go back, and that reduces the current to 2. So the current in this H bar, which is what they use in the experiment, is actually 2E squared over 8. So when they measure 2E squared over 8, it's because they're using the H bar and not this setup. But like Andre said, they have done various different configurations of voltage leads, and you can get various numbers depending on how you put the voltage leads. And apart from being not exactly quantized, it all fits. I wasn't going to mention too much about why it's not quantized, but there are several works. For example, one work which argues that there are maybe, if there are charge puddles next to the edge, then you can get phase breaking because the electron can scatter into the charge puddle and spend a very long time there and phase break and so on. So let's not discuss it. So there's an exercise here for you this evening. Do the calculation in the H bar. So this calculation, I guess you need maybe the... Okay, good. Clear. Questions? Okay. So then I'm going to go into 3D topological insulators. Here's a MARPES. So now, a 3D topological insulator is a material which has a 2-dimensional surface. And that 2-dimensional surface is pretty cool because it has an odd number, and in the case of bismuth selenide, a single Dirac fermion, or a Dirac cone, that describes the surface state. So now if I want to understand the transport properties of surfaces of 3-dimensional topological insulators, which is what I want to do, I have to understand what are the properties of Dirac fermions when I add disorder or what have you. Actually, I only add disorder. I'm not going to do any interactions. So for that, to kind of know what to expect and to understand what is the surprise, maybe, or what is the kind of deep thing, I need to discuss the scaling theory of localization. So let me check. How many of you are experts on the scaling theory of localization? Good. How many of you have never heard of it? Okay. Good. So we can go slow. So there is this plot here, which is not yet here, but I'm going to slowly build it up, which in a sense is a very nice way of understanding results. And it's also a nice way of telling a story. So it has a y-axis, and on the y-axis there is this beta of G, where G is the conductance, which is a d log G over d log L. And on the x-axis there's log L. Okay, so what would such a plot tell me if, so it turns out and will turn out that just the conductance, log of the conductance. Log L. Yeah, you shouldn't listen to what I say, but what I mean. That's right. Log G, very good. So the conductance. So conductance is a function of beta of G. So what would such a plot tell me? Well, this beta function tells me that how does the conductance change if I change the system size? So, because it's a derivative of G with respect to L, which is the system size. And the fact that it logs, don't worry about it, it's just so that that gives me quantities which don't have units. So, if I am now asking what is the conductance of the surface of a very large bulk material in the thermodynamic limit, I would want to know how does it scale as I change the system size. So if the function beta is positive, that means that if I increase the system size, the conductance has to also increase. So if it's positive, that means as I scale, the conductance increases. While if it's negative, it means that as I increase the system size, the conductivity becomes smaller and smaller. So that's what the function tells me. Now let's look at limits where we can actually calculate this. The simplest one is the classical conductivity, which you get at very large conductivity. So then you just get derivative, where the conductance is L to the power d minus 2 times the conductivity, which in the classical case is a constant. It's a characteristic of the material. Now, if I take a derivative of this, I get just d minus 2. I take the logarithmic derivative, d minus 2. So in d equals to 3, that is equal to 1. In d equals to 2, it's equal to 0. And d equals to 1, it's equal to minus 1. Now another limit where we know is Anderson localization. How many of you know what Anderson localization is? Okay, good. Not everyone. But so Anderson localization is the phenomena that a quantum wave can get localized by interfering with itself, the interference being induced by scattering of some disorder. So if disorder is very strong, then the particle just scatters of the impurities, it interferes, and then it gets localized such that it is localized with some localization length psi. If that is the case, then the conductance, if all my states are localized with a localization length, then the conductance has to be exponentially small, also with the same localization length. Now, if I take the derivative of this, I just get log G, so that's lines like this, which I just shifted for clarity. Now, what the gang of 4, these guys, did in 79 is to just say, well, let's just draw a line in between these guys. They were right, but they basically just said, let's draw a line. And then in d equals to 1, we see that beta is always negative. Now, what does it mean that beta is always negative? Exactly, and it basically keeps. I can imagine that the conductance, if I start here and I start changing my system size, it just flows towards minus infinity, which is exponentially small conductance. So in 1D, everything is always localized. In 3D, I have a crossing point here. And what is that crossing point? It's a transition. Because if I start on this side, then beta is positive. I flow here towards large conductivity. That's a metal. If I start on this side, I flow in this direction towards very small conductivity. That's an insulator. So this point is a metal-insulator transition. Okay, good. Now let's throw everything away because actually we were interested in 2D. We were interested in the surface of a 3D topological insulator. So now what happens? How do we connect these two guys? I didn't draw the line before. Any ideas? Suggestions? I just draw a line? Okay, so why am I asking? Why is it not obvious? Well, it's not obvious because I have to go from here to here, but whether this 0 here is approached from above or below will change a lot. If it's approached from below, everything is insulating. If it's approached from above, then just like in the 3D case, I have a metal insulator transition. So we have to know whether we are approached from above or below. Which one do you think? Above? Any other? You want to vote? Well, we have to do a calculation. If the classical calculation gives me 0, I have to do the first order quantum correction to see whether it's positive or negative. So let's do that. Let me give you some definitions which will be useful in the following. So I want to imagine that I'm looking here at the surface of the topological insulator. I have two leads, and I'm passing current between them. I want to know what is the conductance. And a nice way to do it is to use scattering theory, or to think of conductance as transmission. So the larger the transmission probability from here to here, the larger the conductance is going to be. So I'm going to abstract this into this thing. So here's one lead, here's another lead. There is a number of incoming modes coming in here, which I call n left. Outgoing modes on the left are the time reverse of those, and the same on this side. Now, in the left lead, which is x more than 0, my wave function is some linear combination of the in and outgoing modes. On the right, in the right lead, x starts with an L. It's a linear combination of the in and outgoing modes on the right. And in the middle, it's something. And if I wanted to know this coefficient, I have to calculate this something. But just to make arguments, I don't need to know what that something is. All I need to know is that these coefficients, the D's, which are the coefficients of the outgoing modes, are related to the C's, which are the incoming modes, by what's called a scattering matrix, which consists of a reflection matrix, transmission matrix, and so on. And the conductance is just the trace of T dagger T, or through unitarity of S, it's trace of 1 minus R dagger R. So now if I want to know the conductance, I just have to calculate reflection amplitudes. And one way to do this is just to write down some kind of path integral. So to calculate the probability of a wave coming in here, doing something, and then going out again, I'm just going to write it as sum over all possible paths that go from here and go back out here. And there is some phase associated with it, where S alpha is the action of that path. And then there's a coefficient here in front, which is, it will take too long to explain it, but it's just some coefficient. So it's the weight of that path in that sum. Okay? So plugging this into the formula that we had for the conductance, I get N coming from the 1. And then I get R dagger R trace. So I get these coefficients with different sign, and then the two weight factors. Now, if we said we want to calculate the first order quantum correction, which means that we are close to the classical limit. So these actions are very large on the scale of h bar, which means that this is a very rapidly oscillating function. So if I wanted to know what is a classical conductance, I just take alpha equals to alpha prime. So it's that this phase is 0, and I get the classical conductance, which is this. So far, so good? Okay. But there, since we have time reversal symmetry, there are more paths which this phase factor vanishes. Namely, if I can find paths such that the action of alpha and alpha prime is the same, then it will also vanish. Of course, if alpha is equal to alpha prime, it vanishes. That's the classical one. But if I take the alpha tilde, which is the time reverse of alpha, then because of time reversal symmetry, the action is the same. Okay. But that means that once I plug that in, I get A alpha squared. I'm now only looking at the contribution of these two paths to this sum. I get A alpha squared, which is coming from one path, A alpha squared, which is coming from the time reverse of that path. So these are the two contributions that go into the classical conductance. And then I get the 2 times the real part of A alpha tilde star. Now, what is this? Okay, to be honest, I was a little bit sloppy in writing A alpha, but we can physically understand what this is. It's some other thing, which generally, if I have timers, I would expect these to be at least of the same amplitude. So it should be the same amplitude, but maybe there's a sign coming in. And in fact, there is a sign. Namely, if I look at the paths alpha and alpha tilde, alpha does this. It goes like here, 2, 2, 2, 2, 2, 2, and out. Alpha tilde does this in the opposite direction. Now, if I have strong spin-orbit coupling, that means that the spin is locked to the momentum, then the spin rotates for this path. It rotates like this, and for that path, it rotates like that. And since this path comes with the complex conjugate, the total rotation of the spin is 2 pi in that A alpha tilde. What happens if I rotate the spin by 2 pi? Get a minus 1. Which is so I get a minus 1 from the rotation of the spin. If I put a minus 1 here, I get A alpha squared plus A alpha squared minus 2 A alpha squared, I get 0. While if I have no spin, then these will just be the same, I get 4 A alpha squared. So this is if t squared is equal to 1. This is if t squared is equal to minus 1. Okay, so what does this mean? Now think about it. Sorry? For that particular mode, yes. Or absence of backscattering, actually. So if I think about the conductance, compared with the classical conductance, does the first order quantum correction reduce or enhance the conductance? In which case? Yes. Because we're calculating reflection, the reflection probability is smaller than in the classical case, where it's only these two terms. So the conductance is larger. This is what is called weak anti-localization. In this case, the reflection probability is larger because of interference between these loops. The transmission or the reflection the reflection probability is enhanced, so the conductance goes down. So that's what's called weak localization. Now we could have done the same calculation just using a transmission matrices. If you do that, you run into a little bit of a trouble. Namely, if I wanted to take the time reverse of a curve that goes from one lead to the other, which is what I need for the transmission, then I find that the time reverse is not in this sum, because the time reverse goes from the other lead back. This caused some troubles for people doing semi-classics for a very long time, because if I want everything to be current conserving, then it cannot be that the reflection is reduced, but the transmission is the same. That doesn't conserve currents. So the solution to this problem was to find paths which give you the right correction to the transmission. And things are a little bit more complicated here because I have to take paths which cross. And then I have to compare it with a path that also goes from left to right, but has an avoided crossing at this point and traverses the loop in the opposite direction. And if I just calculate the probabilities of all such loops, I can calculate what actually the correction will be. I'm not going to do that now. So this is actually a little bit nice. So now there's a little bit, this is going to be, if you need 1 minute to rest now and you don't care about field theory, you can rest now while I explain this. But if you care about field theory, I think this is kind of cool because I can think about now, I can think about these guys pictorially as being an electron and a hole moving in the same direction. So that's what's sometimes called a diffusion. While here, an electron and a hole move in the opposite direction. And if I allow all possible kind of paths here, that's what's called a Cooperon. And then this crossing is what's called a Higami box. Namely, and you can think of it as an interaction term between the diffusion and the Cooperon. So if I replace these paths by a propagator for the diffusion, this thing by a propagator by the Cooperon, and the Higami box essentially is some kind of interaction between these terms. So with this, I can write down the field theory describing diffusion, which is called a nonlinear sigma model, and I will come to it a little bit before, but I'm not writing it because that would take us way too far. Okay? But it's nice, so you can, if you want to ask later. Okay, so whoever took a 1 minute nap, you can wake up now because I'm going to move on. And I'm going to go back to this. So we were here. We needed to know what happens here. So now we do. If we have time reversal as squares to -1 with weak anti-localization, and I approach from above, while if I have time reversal as squares to +1, I approach from below, I have weak localization, I can connect here. This is always insulating. Here I get a metal insulator transition. Okay. So far, so good. Yeah, all of this, it's important that you have phase coherence. Actually, what really happens is that you really only need the phase coherence for these loops. So if you were to calculate how phase coherence breaks down the weak localization corrections, then it would first kill off kind of the bigger loops, but the smaller loops would still be there and give some contribution. Sorry, can you say that again? Well, I don't know what you mean by weak localization, weak anti-localization transition. So, I mean, this is for a system with t squared is equal to +1. So this is just telling you that the quantum correction makes this metallic phase unstable because I flow away from it. And that always happens. Yes. Yes. Okay. Now this is not, I mean, I spent a lot of time on this because I like it, but it's also because it's not what happens in topological insulators. But how it does not happen is actually very interesting because, I mean, I didn't really use much to derive this. All I needed was that I know the quantum corrections here. And it's important that the quantum corrections are the same in the topological insulator or if this was just some two-dimensional metal. If I take two-dimensional electron gas, which is what you would have here. If you have two-dimensional electron gas with spin-orbit coupling, this is what I get. So what happens in topological insulator? How is this changed? And for that, I have to do a short calculation here. So we had this before. We were trying to understand two-terminal conductance. We wrote down the wave function, and we have a scattering matrix, and the scattering matrix relates incoming waves to outgoing waves. Now, on purpose, I wrote the modes here with the time reverse of the mode. The incoming mode is the time reverse of the outgoing mode. If I have time reverse symmetry, and this wave function is a solution to my Hamiltonian, then the time reversed wave function is also a solution. So if I just take the time reverse of this wave function, and I now remember that t is anti-unitary, which means, as a consequence, that it's anti-linear. We saw this in Alex's talk. Then I have to complex conjugate the coefficients as I go through. Okay? And now this n just becomes tn. When I hit this guy, I get t squared, which is a -1, and the t disappears. So here I can, again, relate the coefficients of the incoming modes to the coefficients of the outgoing modes. And it's just that now instead of being c's, it's d's, and there's a minus sign. But if I take the complex conjugate of this equation, then I will get an equation that looks like this if I multiply by S inverse. And that implies that the scattering matrix is anti-symmetric. Now, what does it mean that the scattering matrix is anti-symmetric? Well, first of all, it means that the diagonal elements of the reflection matrix are 0. That's saying that the reflection back, the backscattering which we calculated in first order quantum correction for the weak localization is always true as long as I have time reverse symmetry. The diagonal elements are always 0. Now what that means for a Dirac fermion is that this state here cannot be scattered into this state here, or how I draw it like this. That means that there's no way for a state to be backscattered. And this is not just one scattering event. It's any number of scattering events that I can think of, because the scattering matrix that we wrote can contain all possible scattering events. It always has to be anti-symmetric. Now, this is also true, for example, this is a two-dimensional electron gas with Raspa spin-orbit coupling, where you have two bands. It is still true there, but it just means that this state cannot be coupled to this state, and this state cannot be coupled to this state. But just as in the quantum spin-Hall effect, now I have backscattering, but I just have to preserve the spin as I do the backscattering. So there's no backscattering at any order. But more than that, if I look at the determinant of the reflection matrix, it is -1 to the power of the size or the number of modes of the reflection matrix. And in this case, where I have only one Dirac fermion, the number of modes is odd. -1 to the power odd is -1. So that means that the determinant of R is equal to minus the determinant of R. That means the determinant of R is 0. If the determinant of a matrix is 0, then that means that one of its eigenvalues is 0. That means that there is one reflection mode which is 0, which means that the transmission is 1. That means the conductance is always at least E squared over 8. It cannot be smaller, just because of the symmetry. That means that instead of having the kind of localized version here, I have instead a positive wave function here. Now I have to connect this to this. And you can guess how it connects. Well, or you do a calculation. So you can write down the field theory, and if you compare the field theory of these two cases, the one where I have only one mode, so the Dirac fermion, which is the surface of a topological insulator, or I take the the two-dimensional electron gas where I have two bands, they differ by a topological term, and it's this topological term in the field theory that protects me here. But actually, I cannot really get that so easily out of the field theory because it's really only valid at strong coupling. So, or at least I don't know how to get it out very easily. You can really argue that there should be no localization here once you have a topological term. But I can also just calculate it. I calculate conductivity as a function of system size. If I take the derivative of that, that's equal to what? What's the derivative of the log of the conductivity when I take it with respect to derivative with respect to log of L? That's the beta function. So what is the beta function of this data here? Yeah, so there's a hint there. It's positive. And actually, here it becomes the weak anti-localization corrections very quickly. It very quickly flows into the weak anti-localization correction. So this is the curve. It says that the surface of a topological insulator cannot be localized. I know that this is a much stronger statement than saying that I just have to have a gapless mode at the surface. Because I can easily fill in the gap with disorder. And I could have imagined I fill in the gap, but I become localized. But that's not the case. As long as I don't do something drastic which completely destroys the full bulk, the beta function is always positive. The surface cannot be localized. And as I flow here, you see this is always positive, so I always go into very large metal if I make my system very large. Okay.
And this is true even for disorder with spin-off decoupling?
Yes, so as long as the disorder doesn't break time versus symmetry, this is true. Yeah, in 1D or in 2D. Oh, so you can connect them from both sides, you mean? Okay. Good. Now, I'm going to skip this one and just summarize this very quickly here because I think we're approaching beverages. So the field theory has this action which has some fields which live in some symmetric space. And that symmetric space maybe has some disconnected parts. And these topological terms just, in the simplest case, just gives a different sign to the fields that live in the different parts. And that protects things from localizing. It's not obvious that protects it. I mean, if you didn't understand that statement, that doesn't matter. What matters is this. I can think of a topological insulator in D dimensions. I can now generalize this result. I can think of a topological insulator in D dimensions as a D minus 1 dimensional surface has a D dimensional one. Let me do this again. So a topological insulator in D dimension has a D minus 1 dimensional surface that cannot be localized. In the quantum Hall effect, it was chiral and just moved like this. It was simple. We didn't really have to do much calculation. I was just reminded of when I was a kid learning quantum mechanics. My teacher had the rule that if a phone rang during a class, then you had to bring cake for everyone next time. I think it's a good rule. The nonlinear sigma model describing the surface correspondingly has a topological term. So you can just take this as a definition. And if you go to this column here, I don't know if you plan to talk about this, but it's probably not. But that's why I actually showed it, because I think this is pretty cool. Often when you first hear about this table, it's this column, which is the topology of the Hamiltonians, which is discussed. But this is kind of nice. It's a topology of the nonlinear sigma model, which tells you whether the surface localizes or not. And if it does not localize, then you know that in one higher dimension, you have a topological insulator. And from that, you can build up this same thing here. Okay. I think that's a good point to end. So this is the summary of this lecture. I think I just said this. So maybe this part, because this will be the starting point of next lecture, is that in this particular case, for the 3D topological insulator, since it's always positive, it always goes to this large conductivity symplectic metal. And in that symplectic metal, I have no everything is determined by weak anti-localization, and I no longer know that it's a topological surface of a topological insulator because all the transport properties are the same as for a two-dimensional electron gas in that limit. Okay? That's a good point to stop, I think. I think the same thing happens in the crystalline insulators. As long as I don't break the symmetry. Yeah. Well, it's not quite that. It's okay. I mean, an example which is not exactly a crystalline insulator, but it gave a surprise is the weak topological insulator, which naively, because there's no topological term in the field theory, you would think localizes, but it actually doesn't, unless the translation symmetry is broken not on average. So I have to not only and some of the same thing happens in the crystalline insulators. So if the symmetry on averaging over the disorder is recovered, that generally is enough to, at least in this case, it's enough to make it not localized. If I break it on average also, then it becomes an insulator. Yeah. No, that's good.